In this video, we're going to look at the post-lab, the heat of fusion. The first question asks, why were the mass of water and melted ice used instead of the volume? There's two reasons for that. First off, the mass was used because anytime we're looking at the equations, whether it be the change in temperature or the change in phase, it asks us for the mass in both cases. So the Q for the change in temperature or the Q for the change in phase. Now, if we're changing phase for the solid to liquid or liquid to solid, it's the heat of fusion. Remember, if it's liquid to gas or gas to liquid, we would be using the heat of vaporization, just a different constant. But in both equations, you're looking for mass. But a step further is, if you look at the CP value, the units of CP are joules per gram degrees Celsius. So it's based off of a gram. If you look at the delta H FUS values, it's joules per gram, not joules per volume. So because it's joules per gram, we are looking for the grams, not the volume. The heat of vaporization also is in units of joules per gram. So when using this variable into this equation, in order to cancel out units, we would need the mass in grams to be able to cancel out each one of these units. So the reason that we use the mass instead of the volume is not only the equation calls for the mass, but if we use the volume, the units would not cancel out. In looking at three sources of error that could have taken place during this lab, one of the sources of error is the transfer of water with the ice. So as we placed ice into the warm water, we could have also taken some water with it, or a change in temperature or change in phase of the ice during the transfer. So we could have experienced a change in temperature or a change in phase of the ice during the transfer into the warm water. And then finally, the last source of error, obviously, not obviously, but another source of error could be energy transferred other than ice. So we said that the energy that's leaving the water must be equal to the energy going into the ice, but it's very possible that that energy might have went somewhere else. For instance, there's energy that's heating the air around the water. There's energy that's heating the cup that's holding the water. So some of that energy could have went into other areas. Using evidence from this lab, explain how calorimetry is a demonstration of the law of conservation of energy. Well, my hope is that when you calculated your percent error for the heat of fusion, that it was a very low percent error, demonstrating that all the energy, and this is not perfect, but we're stating that all the energy that left the water had to go into the ice. That's the law of conservation of energy. Energy cannot be created or destroyed. If energy is leaving the water, it must be going somewhere, and in this case, it's going into the ice. It's going into first melt the ice, and then it's going also into changing the temperature of the melted ice. And that's why we had two equations on this right side. The law of conservation of energy is stating that whatever energy is leaving the warm water is going into the ice. Is the process of melting endo or exothermic? And explain. In a previous video, we talked about the heating curve. And anytime we're moving from left to right on the heating curve, we must be absorbing energy because we're moving from an area of lower energy, such as ice, to to a higher energy, such as vapor. When we are absorbing energy, we are going through an endothermic process. Endothermic, therm for heat or energy, and energy going into. So anytime we're moving from left to right on this chart, we're absorbing energy. In this case, they're asking about melting, and melting is an endothermic process. You're moving from a state of a solid to a state of a liquid. You're absorbing energy, gaining energy, so it's an endothermic process. Why is it better to put ice rather than an equal mass of cold water into a drink? Well, if we look at the heating curve, if we put ice into the water or a cold drink, here's where the ice would be. Here's the same temperature, but you're dealing with, and I'll just call it water, and it's a liquid. So here, if you put ice in, the ice still has to go through a change in phase before it begins changing temperature. But the water at the exact same temperature will immediately start to change temperature. So although it's possible to put ice in at 0 degrees Celsius and an equal amount of cold water at 0 degrees Celsius, the ice will absorb energy before then changing temperature, whereas the water is already in the liquid phase and it will immediately start to change temperature. So it's going to absorb a lot more energy. The ice will absorb a lot more energy before changing temperature, so it will lower the drink temperature more than just water. How would the value calculated for the heat of fusion change if you had used wet ice cubes instead of dry ice cubes? Well, if we used wet ice cubes, really where we are starting on this graph is somewhere right here. That means the process of melting would have already taken place. Because the process of melting would have already taken place, the energy calculation would be incorrect. Therefore, the heat of fusion value would also be incorrect. So when we look at that equation of the amount of energy leaving the water going into the ice, if the melting would have already started taking place, then that calculation would have been incorrect. Question number 7 asks, you can cook vegetables by dropping them into boiling water or placing them in a basket over the boiling water and putting them in steam. Which method would be faster? So once again, we're going to go back to the heating curve. We're going to look at the heating curve. And here is where steam would be. And if it's at 100 degrees Celsius, it could be right here. And then this would also be a liquid at 100 degrees Celsius as if we're dealing with water, which we are. So let's say that we're steam right at this point right here at 100 degrees Celsius. Well, steam at 100 degrees Celsius contains much more energy than a liquid at 100 degrees Celsius. So if those vegetables are sitting in the steam, that steam is going to be giving those vegetables more energy than the liquid at 100 degrees Celsius because the steam contains much more energy than the liquid. So you want to put those vegetables in steam, which contains more energy and can transfer more energy to the vegetables. Suppose you have equal masses of two substances that have different specific heat capacities or initially at different temperatures. You mix them together and wait for them to reach thermal equilibrium. Which substance will show a larger change in temperature? So let's say that we had two substances, a substance A and a substance B. We know that we have M of the substance A, delta T of the substance A, and Cp of the substance A equal to M of substance B, delta T of substance B, Cp of substance B. So it says equal masses, so the masses are the same. Not equal change in temperature, we got to see what the change in temperature is going to be. So let's say that this is a large value and this is a small value. In order for, since the masses are the same, they cross out. In order for this times this to equal this times this, if this is large, this must be small. If this is small, this must be large. So a small Cp value will give you a large change in temperature, and a large Cp value will give you a small change in temperature. We saw this with the lab with the water and the metal cube. The metal cube had a very small Cp value, so it had a very large change in temperature, whereas water had a very high Cp value, so it had a small change in temperature. I hope this helps with understanding the post-lab for the heat of fusion.